So the work I'm going to present today is about zero-size heap allocations. So, since 10 years or so, we have lots of software vulnerabilities due to heap overflows and everything. So zero-size heap allocations are one instance of potential heap overflow. How many of you guys do C programming? Good. So this talk is rather technical, so if I'm too fast or maybe too slow, just let me know because I want everyone to get it. And there are going to be lots of examples, so hopefully it's going to be all clear for everyone. So even though most of this work has been done on Microsoft code bases, so mostly we're going to present examples on the Windows kernel. This is not a Windows-specific problem. This is present on Unix operating systems as well, on mobile code as well. So in this CCC, we've had lots of talks about infrastructure attacks and everything. And by the way, thanks for the great event because it was really interesting to attend all those talks on GSM and stuff. And we're going to be at slightly at the highest level here, since we're not going to touch to the infrastructure, but see what happened at the application level. So we're going to see the kernel stuff, we're going to see a couple of application stuff, and keep in mind that it absolutely applies on mobile, not only Windows Mobile, but also whatever mobile operating system you wish. So let's get started. So what is a zero allocation? Obviously, you know that you have dynamic memory allocators on all desktop operating systems. So whenever you need to allocate memory dynamically, you call a function malloc. So malloc takes a parameter that is the size of the memory you want to allocate. The thing is, when you put a size of 0, the behavior is implementation defined. So it's not specified by the ISO C99 if you either need to return a null pointer or if you need to return a valid pointer, etc. So it's basically up to the implementation. So as we will see, most of the time when you do a zero-size heap allocation, the malloc function and also many other functions that allocates memory dynamically, they return a valid pointer that is pointing on a valid heap chunk. So for example here, we allocate 0 bytes, the pointer is not null, so the check is not sufficient. And if you have a side condition, say an integer underflow or overflow, in that case the underflow size -1, then you have a buffer overflow, and checking the pointer for null is not going to save you from anything here. Second example, you have an arithmetic operation, say a multiplication or even addition. The thing is, the result can still be 0. Say in that example, data arrow NBR is 0, multiplication gives 0, so the size stays 0. You allocate 0, you test for the pointer null again, but no error is reported. And then you dereference the allocated pointer to an invalid location. So in that case, you're going to try to write to an invalid location, ptr arrow field. Third example. So here you read the size from an untrusted location and you add the size of a structure, say the size of a header, for example. You allocate, and then you check for null again. And here, so it's a pretty obvious flow again, but can you understand why this is potentially buggy? It's basic, right? Well, if you have an integer overflow, then you can have a size that is small, and then potentially 0, potentially small, maybe 1, maybe 2, you don't know, it depends on the size of type, and depends on the untrusted value as well. And here you trigger again a heap overflow. So this third scenario is not specific to zero allocation. I mean, it could be the classic, this is a known case of integer wrap and allocation, so it has been discussed a lot before. However, our characterization of zero allocation also handles this case, so it's a generalization of the integer wrap case. So any questions so far? I know we just started, but maybe we want to discuss things. Okay, all right. So yeah, zero allocations, in my opinion, are not a new kind of vulnerability. Those are more a new kind of technique to find a specific class of heap overflows. So because buffer overflows in the general case are very hard to get rid of, we want to restrict the attack surface to something that is tractable, that is only the cases where the size could potentially be zero. So even big code bases, this is potentially a small number. I'll give you some numbers later so you can realize exactly. And also in Microsoft, we do lots of analysis. So we do lots of static analysis, we do lots of fuzz testing, we do lots of code review. So we have a small internal tool that is based on a theorem prover that allows us to uncover all those locations in the Windows kernel and actually any code base. So that allows us to filter out the code review we have to do, since we have to review many millions of lines of code. This is very practical to actually be able to give a higher insurance of the absence of such particular bugs. Something I should say is that our tool works mostly for C programs, so we do that from the source code. It's possible to do that at the binary level too. However, since we have the source code, we just don't bother, basically, and it doesn't make sense when you're in Microsoft to do binary analysis, so we do everything on the source code. The support for C++ is a work in progress, so we start to target C++ programs as well, such as browsers and stuff, but it is going to be for later, not for this talk. Okay, so a little outline of the presentation. So first of all, I'm going to run a couple of tests so that you can see what is the actual result of zero-site heap allocations on a couple of kernel functions of the Windows kernel. And then I'm going to introduce 3 different techniques for detection. So all I'm going to talk about is static analysis. So we had a couple of talks on dynamic analysis, how to detect this in runtime and everything. This is not what we're going to talk about. So all the detection that happens here is done without execution. It's done only by compiler plugin. So at the build time, we are able to detect all those instances of potential zero allocations and where memory corruption can happen. So the tool is called HAVOC. So it's developed at Microsoft Research Redmond in the research in software engineering team. It's a team of Thomas Ball, who had a couple of success in the last 10 years with automated tools such as SLAM, the SLAM model checker. It has been very successful on small scale. So when I say small scale, it's about drivers of up to 20, 30,000 lines of code. Here, we don't use a model checking as in SLAM. We're going to present a technique based on theorem proving. I'm going to give a couple of examples of this later. And as the last part, I'm going to generalize the property of zero allocation. So sometimes you don't have a zero allocation, sometimes you have a near zero allocation. So if the size holding variable can be desynchronized compared to the size of the allocated memory, even though you don't allocate 0 byte, you can still have a couple of problems. And I'm going to give one example of bug we haven't covered. Okay, so is your environment exposed? Let's see on Windows, for the Windows kernel. We have a function in the Windows kernel called xallocate pool with tag. So xallocate pool has a couple of associated API. Basically, the first parameter of xallocate pool with tag is the size, and just ignore the 2 others. But when you call xallocate pool with a 0 size, it actually returns a valid pointer, as you can see on the right side. This is just a dummy kernel driver I wrote. In fact, if you look at the code, at the binary code for this function, you can see that whenever the number of bytes you have to allocate is 0, you actually put the size to be allocated to 1. So when you do a 0 allocation, you have every time, most of the time, you have a couple of bytes that are allocated. So for the case of the Windows kernel, this is 16 bytes, because you can see that if EDI, the EDI register is 0, then it's incremented, and then it's rounded up. So rounded up plus 15, which makes 16. So it means that if you do zero allocation, sometimes it's not a bug. Sometimes nothing happens. If you don't touch the pointer, nothing happens. If you touch the memory below 16 bytes, nothing happens. However, if you dereference the field of a structure that is beyond the 16 bytes offset, then this is where you start to have memory corruption. Couple of tests for userland. So on Windows, you have mostly 3 userland functions to allocate memory: malloc, heap-alloc, and virtual alloc. So virtual alloc is the most low-level function that is called by malloc and heap-alloc. And malloc is used for C programs, while heap-alloc is used for C++ programs mostly. So same thing, you can see here that the return for malloc and heap-alloc with a 0 size is not null. So it actually returns a valid pointer. However, virtual alloc, which is very rarely used directly, returns null. So the risk you have if you just use virtual alloc is to have a null dereference, but it's not very interesting in userland. Other operating systems. For Linux, same behavior. Linux with PAX, same behavior, except for kernel-land. So PAX introduced a very nice mitigation for zero-size heap allocations in kernel. Basically, by default, the kmalloc function on the Linux kernel returns 0x10. So it's vulnerable to null pointer dereference kind of attack when you map the null page and everything. So it's not a very good idea to return 0x10 by default, because you can still have a dangling pointer. When you have the PAX patch that is part of GRSec, they change this value to FFFFF000, which is the address of the first byte of the last page of the address space. So whenever you touch this pointer, and I should say that this page is unmapped. So whenever you touch this pointer, you just touch unmapped memory, and so nothing can really happen. You just crash the kernel, you cannot exploit anything. For other operating system, all of them are also exposed. On FreeBSD userland, the malloc function, when you call it with a 0 size, return a constant that is 0x800. So don't ask me why exactly they return 0x800, because it doesn't seem to be any specific value. Maybe someone knows? A FreeBSD developer in here? No? Okay. Anyway, this makes zero allocation in userland and FreeBSD unexploitable. Because, well, unless, of course, you know how to exploit null pointer dereference in userland, which I don't know, since null pointer dereferences are mostly exploitable in kernel. Yes? Are you talking about userland or kernel-land here?
It's on, but okay, jetzt it's working. Okay, so I'm thinking about PC architecture in general, because there are some magic numbers in the old PC architecture, because there were some dirty hacks in earlier time that were always used until today, because everything has to be compatible to the old original PC. And so maybe this number you have to find in Etherbox or somewhere, maybe it has something to do with the MMU, that it will block memory or something.
I don't know. As I said, I don't know exactly the reason for this number. If you look at the runtime dynamic linker or something, or like maybe the allocator for FreeBSD userland, maybe you can get the reason without too many too much effort. However, it's a detail. We can talk about it later. On other operating systems, Solaris. Solaris is kind of interesting because you have multiple API to call to do a dynamic memory allocation in the Solaris kernel, but there are APIs in Solaris kernel. When you call them with a size 0, it actually returns null. And in the Solaris kernels, many times you will actually, yes?
Isn't that because